Just right there. You can have the mic if you want.
Oh, there's another one, sorry.
It's okay.
Hi everyone, my name is Aline. Thank you very much for coming to this talk on photonics for astronomical instruments. I've had a very exciting week here. I've learned a lot about exoplanets. So let me try to tell you a little bit about astrophotonics. So I will start with a little introduction and then talk about manufacturing methods, since they are very important, and give you some examples of different components and devices for different applications, and then a specific focus on astrophotonics for interferometry that we've just heard about, because this might become even more important for exoplanet detection. In general, astrophotonics describe chip or fiber-based photonic components that can be used at different points in the beam path in an astronomical instrument. So this can, for example, be used to filter out unwanted emissions in the atmosphere that we've already heard about, or we can use AWGs, gratings, to disperse the light, or use photonic beam combiners in interferometry. And photonic components are particularly well developed in the near-infrared because of their heritage in the telecommunication wavelength. But this is also starting to expand. And near and mid-infrared photonic components are particularly going to be important for the next generation of extremely large telescopes, including the ALT. And they can help to avoid having extremely large instruments just because our telescopes are extremely large. And similarly, for interferometry, if we expand the number of telescopes, which means we have increasing numbers of beam combinations for interferometry, photonics can also help to keep the optical layout limited. And expansions are planned both for the CHARA and for the VLTI, and CHARA already has a 7th telescope that they're currently being installed, and as well as new constructed interferometers that have up to 10 telescopes. And due to their physical dimensions, photonic components are particularly suitable candidates for future space missions. And the physical dimensions, of course, come with the advantage of having the potential to reduce the size, the weight, and the cost of an instrument, and in particular this last aspect is very important for all of us. And because they're very often monolithic, so they can be just a block of glass, for example, with some interfaces, they have the potential to be more stable against environmental effects that we've already heard about a lot. So temperature changes or vibrations might be able to be mitigated a little bit. And if you have the right interface, for example, fibers, you can also plug and play and also potentially replace a component with an updated one that has more functionality, or even extend it down to having a complete system that consists of a bunch of connected photonic components. But it's not just the physical properties that make photonics quite useful for astronomical instrumentation. So there are some unique properties of photonics that are very difficult or even impossible to simulate with free space optics. And one of the unique properties that you can maybe just reproduce with a pinhole is the spatial filtering that we've already heard about a little bit. So maybe for that, I'm going to go one step back and just talk about the foundation of photonics. So what I mean is that we have a waveguide. This can be a waveguide in a photonic chip, or it can be inside a fiber. And a waveguide basically consists of two regions. The center region, the core, has a different refractive index than the surrounding material, which is, in a fiber, it's called the cladding. And depending on the geometry and the refractive index difference, it can support different number of modes of light. And here is a little overview of the different number of the different modes of light, the different linear modes of light. And we have on the very left here, we have the fundamental mode, which is similar to a Gaussian. And if you have a single mode waveguide, so if the waveguide is very narrow, it can only support the fundamental mode, so only the first Gaussian mode here, which means that everything else is filtered out. This can then lead to a reduction of phase errors, and you have basically a transfer from phase noise to maybe a little bit of amplitude variations, but it can help you to get much more precise measurements. And on the other hand, if you have a larger waveguide, you can support more modes. This is called a multi-mode waveguide. We can also have a mode conversion with a photonic lantern that I will talk about in a little bit. Whoops.
Sorry.
Yeah, okay, sorry. And the other thing that we can that's very difficult to reproduce with free space optics is to have bends and curved waveguides. You can maybe have a black hole or a very large object that bends your light, but otherwise it's quite difficult in free space. And if you bring two waveguides very close together, you can also have utilize the evanescent coupling effect. So the evanescent wave can be used to transfer light between waveguides. And I will talk a little bit about the manufacturing because we are working on such small scales that the precision of manufacturing and the method of manufacturing can really influence the performance of your component. There's a bunch of different manufacturing methods, and I'm not going to talk about all of them, but you have crazy things like now 3D printed microlenses on top of a facet of a chip. You can also heat and taper glass. But what I'm going to talk about very briefly also, is the lithographic and the direct laser writing. Lithographic methods are maybe the most mature methods to fabricate something because we have a lot of heritage also from other industries or other applications. And the main thing is that you have to have your whole design on a mask. So you have to know where your waveguides are, you have to design your whole chip, and this design is then transferred using several different steps onto your material. The choice of material, as usual, is of course wavelength dependent. And here's just an example of a mask and of the final chip. This can produce very reliable components, and it has quite a high confinement for the waveguides, but it does take a while and it's quite costly. So if you want to make a design change, if you realize something was wrong, you have to make a design change, you have to do the whole process again. Slightly different approach is direct laser writing, which has many different names. I call it ULI, ultra-fast laser inscription. And the basic principle is that you have a femtosecond laser that is focused onto the glass substrate, or better inside the glass substrate. And in this focus, the refractive index can be changed very locally, so on the micrometer scale. And you can move the sample. I will show you a little video. The sample is moved relative to the focus, and three-dimensional structures can be written within seconds or minutes or days. So this allows for rapid prototyping. If you want to make a change, you can immediately have your design and get your component ready. But to first get the thing to work is not easy. To first find the parameters in this huge parameter space to get waveguides, it's very, very hard. So if you find a group that has it figured out, be nice to them, hold on to them. They can do incredible things. And if they know what they're doing, it opens a whole new world of potential photonic components. So it's really fascinating, and you also have new materials compared to lithographic techniques. But yeah, it's a challenge to get it right, and there's only a limited amount of people in the world who can really do that. So now let me show you some examples. I will restrict myself to 3 examples. There's of course many more. There's also many more versions that might use slightly different ways to produce them. We have photonic lanterns, arrayed waveguide gratings, and reference frequency comms. These are examples mainly from our group at AIP, but of course there's also other groups doing similar things around the world. So we've heard a lot about the effect of the atmosphere on the wavefront, of course, and adaptive optics can help to make this mess that we get into something slightly better, but of course we ideally still want to have the perfect wavefront, in particular since we need good coupling into our single-mode photonic components. And one device that can help is the photonic lantern. The photonic lantern, despite its name, is not actually actively glowing. It just has the shape of a lantern, but it's a passive device. It consists of 3 parts, sorry. First, you have the input region, which is multimode, which means it can take a lot more modes of light, and therefore it might be able to couple with higher efficiency even a partially corrected wavefront. You then have a transition region here. And in this transition region, if you make it long enough and if you have the right parameters, you can then transfer several modes of light into a large number of individual single mode outputs. So at each output, you can then add your photonic components or use the single mode light with a nice perfect wavefront. Here's just an image from one of such photonic lanterns. You have a fiber bundle, it can be tapered down, and you can see here at the end, before that you can still see individual fibers, but in the end it's just melted together to produce a new multi-mode core. And at the other end you have the patch cables that you can just hook up your photonic components to. And we've heard this before in the adaptive optics talk. There's a lot more that we can do now with photonic lanterns than was initially thought. So now they can also be used as wavefront sensors, and there's active research going on. I would like to refer you to this Astrophotonics roadmap if you want to find out more about this. The second device that you could, for example, add to a photonic lantern, to the single mode outputs, is a spectrograph. In this case, I'm talking about an arrayed waveguide grating, AWG, which is a spectrograph on a chip. And since you have single mode inputs, you can make it very small and compact, so you don't need to have a huge meter scale grating, for example, in free space optics. Instead, you have a small centimeter scale device. You have inputs at the heart of the chip. There is an array of waveguides, hundreds of waveguides that all have incrementally different length. And due to that, at the output, there's a free propagation region here. Due to the phase differences, that light interferes in such a way that you have a wavelength-dependent location of the output. And then you can cross-disperse it and look at the spectrum on your camera. Here's an example of such a chip. Of course, it has to be also fiber connected. Then you can get your outputs. And these are just some numbers from example chips. There's a lot more out there from AIP, from our group. And we get resolving powers. Depending on the design, we can achieve 10 to 30,000, which is medium to high. And finally, this high-resolution spectrographs, especially for applications such as precision radio velocity measurements that you need for exoplanet detection, you also want to have a ruler. You want to have a reference. Otherwise, you don't know where your spectrum is actually going. And one of these examples that can avoid the kind of uneven patterns of spectral reference lamps is a frequency comb. A frequency comb produces a very evenly spaced output pattern in frequency like this. So basically a perfect ruler. And it can be produced in a bunch of different ways. The one that's most suitable for astronomy applications due to the spacing is the ring resonator. So we have a chip-based ring resonator. Laser light is coupled in, goes into the ring, and produces a pulse train, which then produces this nice frequency reference spectrum. So these were some examples that can aid also in general astronomy, but also for the detection of exoplanets. And I want to show you some examples of beam combiners in particular for interferometric applications that we've already heard about earlier. So I'm going to rely on Guillaume's nice talk earlier, but so just give a little bit of a recap. So interferometry imitates a very, very large telescope, so it can achieve very high angular resolutions by interferometrically combining light from different telescopes that are separated by a certain distance that's related to the baseline B. So we can achieve higher resolutions if you put the telescopes further apart. And from the interference pattern that you see here, we can get information about the coherence. And from that coherence, we can get information about the intensity distribution of our object in the sky. So that means, for example, precise measurements of stellar diameters, of course, direct imaging, astrometry, or, for example, the study of exozodi. All of these can help with the exoplanet detection. And that's a bit abstract maybe, so how can we actually make any measurements? We need to vary our baseline, for example, by using several different telescopes that have different distances and measure our visibility. The visibility is another term for the interferometric contrast or for our coherence. And by changing this baseline, we then get data points and we can fit a model. So either we can compare different models or we have a free parameters. In this case, we have two different diameters and we can get information about our object. If you have enough measurements, you can also reconstruct whole images. And these are reconstructed images. The only images of surfaces of stars other than the sun are being made with interferometric methods. So you can also recreate images of protoplanetary nebula and other objects. And I just want to point out that you can use different telescopes, but similarly, this also applies, a lot of what I'm showing you and also the techniques also apply to a single aperture that is divided into sub-apertures, and we will hear more about this from Steph in the talk afterwards. And the second thing I want to mention is that the number of beam combinations drastically increases with the number of telescopes. So we have n times n minus 1 divided by 2 beam combinations. So for 4 telescopes, we have 6 beam combinations. For 6 telescopes, we have 15 beam combinations. That quickly gets very, very crowded in your optics lab. And this makes beam combination so important, and this also shows why photonic beam combiners have such a huge potential. And you can, of course, use free space optics, and the alternative is to use 2-dimensional planar or 3-dimensional photonic beam combiners. And I talk a lot about how much I like photonics and how awesome it is and what the potentials are, but maybe this is a good point to also mention that there is obviously some advantages to using free space optics, and you have very high accessibility, but 2 other things are maybe more important. You have also a very high transmission. So photonics, there's still room for improvement, let's say, to achieve higher transmission, especially in astronomy where every photon counts. So that's still work in progress, but it has been rapidly improving. The second thing is that in free space, you can have a whole, a very, very broad range of wavelengths. And with photonics, usually the functionality or even the material is limited to a few hundred nanometers maybe. But because they're so small, you can also stack several of them next to each other or on top of each other. So there's also ways to go around this. I will show you some examples of beam combiners. In particular, I want to show you one example, the Chariot beam combiner that was recently tested at Chara, and we're quite happy with that. So that's a brand new result. And I'm going to just go back again one step to talk about the fundamental principle, which is the directional coupler, or this evanescent coupling that I mentioned earlier. So this is the foundation of all of these photonic beam combiners. You have light at either 1 or 2 inputs, and then a region where the 2 waveguides are brought very close to each other, for example, on the order of 10 micrometers, and the light can couple either completely to the other waveguide or 10%, 50%, whatever you design it to be, and it depends on a bunch of factors such as coupling strength, but also the distance between the waveguides and the length of the whole device. So you can design it to make you a 50-50 beam combiner or splitter. And of course, this doesn't only apply to 2 waveguides, but you can even have a whole array in 3 dimensions so that light couples to all of the surrounding waveguides. And this is used for the discrete beam combiner, one of the 3-dimensional realizations. In 2 dimensions, usually because you're planar, you can't go in the other dimension. You have a cascade of different beam combiners, especially if it comes to combining more than 2 inputs. You have to have several of these combiners in series. And this is a particular case of the ABCD beam combiner. This is also used in gravity, this dial, where you have a phase shift. This will be important later for nulling as well. You have a phase shift, and that allows you to sample the fringe in one shot. So instead of scanning a line, scanning one of the arms, you can have one shot and record a whole fringe and get your information that way. These are just some examples of existing photonic beam combiners in the 3D. Here, you see the size of the glass chips. You have 6 inputs here, 4 inputs underneath. Oops. And similarly, 6 inputs and 4 inputs for the planar beam combiners. And you see the nice output of one of the arms here at the bottom being moved, and you see the interferometric outputs that are then measured and analyzed. And now I just want to show you a very recent result. This is the very first ULI-written beam combiner for the K-band, so for 2 to 2.5 micrometers. And it was fabricated in infrasil glass, which does not have these unwanted absorption features that fused silica has, so the choice of material is really important. And it was fabricated by Harvard University and fiber interfaced for easy plug-and-play operation. That's a centimeter scale chip here. And we've done some calibration and analysis in the lab. And then we felt quite confident because our interferometric results looked quite good, and we went to Chara to replace, the plan was to replace the old JuFlu. You might have heard fluor from the exosodai surveys, to replace a broken beam combiner in JuFlu, but of course it wasn't that easy. So other stuff broke, other stuff had to be changed. We spent weeks and months setting up basically a whole new experiment, a whole new instrument. So this is now called Chariot, to acknowledge this fact. And we have a nice new camera, the Series 1 camera here. Here's our beam combiner in this little red box. And after a lot of calibration, we went on Sky and we saw our first fringes a few weeks ago. And this is exactly, I think, the point that Guillaume mentioned earlier. If you don't have a fringe tracker, the signal just jumps around due to atmospheric effects. And yeah, so if you had to integrate, this is just very short integration time, very bright target for a proof of concept. If you had to integrate, this would not work. So of course, there's a lot of plans. We still have a lot to do to improve our setup, and we also want to integrate a fringe tracker and so on. But these are very nice results for us. So the final technique I want to mention is the nulling interferometry, which might be particularly important for exoplanet detection. It works very similar to regular interferometry, only you add a phase shift, so that the star is in the destructively interfered part, and you can observe the planet. I'm not going to talk more about this technique. There's a few references if you want to find out more. It's a whole topic in itself. But what I want to show you is some examples of photonic solutions for these beam combiners. And I mentioned the phase shifter earlier. That is also important for nulling. So the glint instrument, the glint beam combiner, has both the beam combination part as well as a phase shifter in the same chip. So it operates in the H-band at Subaru. We also have work ongoing for the NOT that we've already heard about. The NOT nuller, which will have a photonic component produced by ULI, but it's a bit longer wavelength. This will be part of the ASGAT suite for VLTI. There's also several fiber-based solutions, some existing ones and some brand new developments, some of them even happening here at Caltech. And we also have a poster on the fiber nulling here, so check it out. And we already heard about the proposed LIFE mission, which will cover a very, very long wavelength band in the mid-infrared to detect biosignatures. And the plan is, or one possible solution is to use photonics, but especially for this broad, very far wavelength range, there's a lot of technology developments that still have to be done. And this is just a little map of existing photonic beam combiners. It's not actually that many, and you can definitely see the heritage in the H-band and the telecommunication wavelength with a bit of the K-band, and additional explorations of the other wavelengths are happening right now, which are predominantly made with ULI due to the different materials as well. So this is the summary now. So I hope I could give you some idea of the different photonic components that are out there, and we've heard how important it is to understand your instrument. And hopefully, if you have to have an understanding of your instrument, or if you want to design an instrument, maybe this gives you a starting point to look into each of these components in a little bit more detail. Of course, each component is its own topic, so you can find a lot of different solutions for that. And I would also like to point you at this astrophotonics roadmap, where a lot of the topics that I have not even covered, such as also active photonics, they are covered there in a bit more detail. You can find the current status and potential solutions. There's also a bunch of overview papers that you can look at if you want to know more about this topic. And if you want to know more about what we're doing in the astrophotonics group at AIP, check out our website or talk to us. And if you're in the area, come and see us. And that's all. Thank you very much.